Let's talk about vertical asymptotes and holes in rational functions. So you can see all the examples I'm going to do in this video. We'll end with this one at the bottom here. We'll talk about the vertical asymptotes and holes in each of these rationals. So let's start with x over x minus 3. So what we always want to start to do is look at the denominator and figure out what values make the denominator equal 0. So x minus 3 equals 0. We add 3 to both sides, and we get x equals 3. So this is a domain restriction of this function. And for a rational, we kind of know how they work. They're either vertical asymptotes or holes. So in this case, 3 is a number that you can't plug into the denominator. Nothing else weird is happening. So we have a vertical asymptote at x equals 3. I say x equals 3 instead of just the number 3 here, because this is really the equation of a vertical line at x equals 3, not just a particular point, making an asymptote in the graph. Right. In this next example, we can see the difference between a vertical asymptote and a hole in the equation. So first we notice that if we set this denominator equal to 0, we can have individual parts set equal to 0, and we get two solutions. We get that x equals +1 and -5 are domain restrictions for this function, but one of them is a vertical asymptote and one of them is a hole. And the key is seeing that is the x minus 1s that are in the top and the bottom of this rational. So because these essentially cancel each other out in the formula, x equals 1 is not creating a true vertical asymptote. It's not making the denominator shrink to 0 and making the asymptote happen. Really, this is just a hole in the graph. Whereas x equals -5, its factor doesn't have anything canceling it out. So this is a true vertical asymptote at x equals -5. Let's look at another example. We have my third example here. So again, we can look at this denominator and pick out the x values that make it equal 0 just by setting each of these pieces individually equal to 0. So this first one gives me x equals 0. X minus 2 squared tells me x equals 2 is a domain restriction. This isn't directly related to the exponent of 2 here. That doesn't affect us in this current decision making. And then finally, x plus 6 equals 0 gives me x equals -6. And now if I look to the numerator, the only one that has a canceling factor up top is the x plus 6. X and x minus 2 on their own are not present here. So that makes -6 a hole in the graph, and then the other two are vertical asymptotes. My final example here, I wanted to mention at the end, because all the examples we've done so far have come pre-factored, right? Everything in the numerator and denominator is factored as much as possible here. And that's what we need to see to make these decisions about vertical asymptotes and holes. So when you're presented with a rational function like this one, and it's not factored, that's now your first step, is to just factor the top and the bottom so that you can see what the factors are and if any of them are canceling out. So we'll start by factoring x squared minus 2x minus 15. I need two numbers that multiply to -15 and add to -2. -5 and +3 will do it, either order. And then on the bottom, I can just pull out an x and I get x times x plus 3. And now I can see that the x plus 3s are canceling each other. So here I have x equals -3 as a hole in the graph. And then from that plane x, I have x equals 0 is a true vertical asymptote because it's not canceling with any matching factor in the numerator.